Hey guys, Jake here, coming at you with another math lesson today. I'm thinking I'm gonna try something a little bit different here on my channel for a bit. Trying to go with a little bit more of a kind of conversational, casual approach. Not worry so much about the production of the videos, the editing, all that kind of stuff. But, really just focusing on the value of teaching how to do math and making sure that you guys are getting through pre-calculus, whatever the case is. I've got some other content ideas that I've been working on that will probably be coming out with a little bit more in the near future. But I just want to kind of get more content out there to help you get through math and help teach you. So going to be taking a little bit more of a casual conversational approach on some videos, see how things go. If you like the new kind of format, if you like the new style, definitely leave a comment down below. Definitely appreciate the feedback. If you want me to go back to the way things were, let me know that as well. But if you do have questions as well, as always, drop them in the comments. I did recently come out with my pre-calculus study guide. If you want to check that out, you can go to jakesmathlessons.com/precalculus-study-guide. You can also scan this QR code here if that's easier for you. But today we're going to be talking about the rational zero test and how you can use that to find zeros or roots of a polynomial. So I just want to start off with an introduction of what the rational zero test is and kind of explain a little bit more of, the thought process that you want to go through if you read a definition like this in a textbook, because I think that's a helpful skill to develop that, typically on my channel, I've really just focused on doing practice problems, which obviously is helpful, but really what's really going to help you take your math knowledge to the next level is learning how to learn this stuff on your own. And learning how to read a textbook is super important for that, because if you know how to read a textbook, you know how to interpret the language in a textbook, you can teach yourself anything just by finding the right book. So that's really what I want to go for here. So let's start with this kind of definition, explanation, what you might see in a textbook. Maybe your pre-calculus textbook even has this exact same explanation. So if we have so if the polynomial function f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, and so on, has integer coefficients, every rational zero of f has this form, p over q. So let's stop there. I want to just kind of talk about this for just a second. This right here, f of x equals this whole thing. It's a weird notation for a lot of people. Understandably so. When you're first looking at this, it looks like a weird puzzle. But basically what you want to keep in mind is this is just a polynomial where you have a bunch of x's. So x in this case is your variable. You know that because it says f of x. So f is the name of your function. Your function is named f. X is the input variable of this function. So we have a bunch of x's in here. In this case, x is the variable. X is your input variable. When you plug in some number for x, you're going to put it in for these x's. These a's, the a sub n, the a sub n minus 1, the a sub 2, the a sub 1, the a sub 0, these are all constants. So these should be thought of as just numbers. You could imagine, like, for example, 5x to some power, 4x to some power, 10x to some power, right? So the x is your variable. The a sub n minus 1, a sub 2, a sub 1, the different subscript is really just to tell you that it's a different constant, right? Instead of saying like a, b, c, d, e, f, g and going through the alphabet, they instead just use this subscript to number it. But each a is just a different constant. It is also possible a sub n and a sub n minus 1 could be the same constant. You don't know. That hasn't been given based on this definition. Really, all this definition is saying is you have some polynomial where you have these different coefficients. We don't know what they are. That's really not important. It's going to work the same either way. And then you have a bunch of x's raised up to some power. So then we have this n minus 1, this second power. The x term and the constant term don't have powers, but you can imagine a bunch of different x's in between here with different powers. So n is just saying this is an n degree polynomial. The highest powered x is the number n. So again, n, n minus 1, those are just numbers. Just like these coefficients, a sub n minus 1, those are just numbers. The only variable, the only real letter here is x. All these other a's and n's, these just represent numbers. So the reason why, you see it written like this is kind of a generic form of a polynomial where you have x raised up to some power times some coefficient. and then a bunch of those being added or subtracted from each other. So that's all a polynomial is. So in this case, it tells us that we have integer coefficients. So in this specific example, this specific rule that we can use for a bunch of different examples, I should say, we have a sub something. So these a's are all integers. An integer is just a whole number. 1, 2, 3, could be negative, -1, -2, -3, so on, right? It could be any whole number. It just means it's not a fraction or a decimal. So we have a bunch of integer coefficients. Now, based on that, that's basically just the setup. We have a polynomial, we have integer coefficients, we have, that polynomial degree is n. It's going up to a power of n. What we know is that if we take p and q, so where p and q have no common factors other than 1, p is a factor of the constant term, a sub 0, and q is a factor of the leading coefficient of x to the n. So basically the highest power x, the leading coefficient. So essentially, all this whole rule is saying is if we take the leading coefficient of our highest powered x term, so this x to the n, whatever your highest power of x is, and you take your constant term, so the one number that's by itself with no x's. You take those two coefficients, so you take this a sub n coefficient, you take this constant number a sub 0, you can use those two numbers to figure out all the possible zeros of this entire polynomial, okay? So let's go through an example. I'll show you what this actual process looks like so I can show you, what this looks like. But basically, you really just need to figure out your highest powered x coefficient, your constant term. Those two numbers are going to be used to figure out all the roots of this function, all the rational roots. Okay, so let's go through an example. We're going to find all rational zeros of this function f of x equals 9x to the fourth minus 9x to the third minus 58x squared plus 4x plus 24. Okay, there's a lot here. A lot of terms, a lot of high numbers, high coefficients. Really, all we need to do is figure out what is your highest powered x term. You can see right here, x to the fourth. This is our highest powered x. And what is our constant term? So this right here, this is our constant term. It has no x's with it. We don't really need the highest powered x term. What we really need is the coefficient. So in this case, x to the fourth is our highest powered x term. What we really want is the coefficient 9. And then we want the constant number out here, 24. So we have 9 and 24. Let's go back to this rule here, the rational zero test. What does it tell us we can do with that? So we're going to basically figure out all of our p's and q's, which is just going to come from factors of this 9 and this 24. Okay? So the q is a factor of the leading coefficient, so the 9. So the denominator is going to come from the 9. The constant term a sub 0, the 24, those are going to be the factors of our numerator. Okay? So the constant term is going to go into the numerator of the fraction. So the 24 is going to go into here. The denominator is going to go as the highest power x coefficient, so 9. Okay, so this fraction by itself is not helpful. Okay, we really don't need 9. We don't really need 24 over 9. I'm just writing that as a placeholder so we can remember the 24 is going to contribute to the numerator of all of our zeros, and the 9 is going to contribute to the denominator of all of our zeros. Okay, so now what we have to do is we have to figure out the factors of 24 and the factors of 9. So that's probably a better way that I can write this, right? We're going to say factors of 24 and factors of 9. Okay, and we're going to make a bunch of new fractions out of those factors. So the first thing we want to do is figure out what are the factors. Okay, so the factors of 24, what are all the factors of 24? The factors of 24 are 1, 2, right? Because 2 times 12 gives us 24. What about 3? Is 24 divisible by 3? Yes, it is. You divide 24 by 3, you get 8. Okay. What about 4? Is 24 divisible by 4? Yes, it is. You divide 24 by 4 and you get 6. Okay. 5, no. 24 divided by 5 is not a whole number. So keep that in mind. We just want whole numbers here. And then now we're up kind of to the other side of it, right? Because I said 24 divided by 4 gives us 6. So that's our next factor. 24 divided by 3 gave us 8. We know it's not going to be divisible by 7. And then 24 divided by 2 gave us 12. We could double check. It's not going to be divisible. 24 is not divisible by 9, 10, or 11. And then it's not divisible by any number bigger than 12 up to 24. So these are all the factors of 24, okay? Then we have to figure out the factors of 9. So obviously 1 is a factor. 1's a factor of everything. 9 is not divisible by 2. It is divisible by 3. If you do 9 divided by 3, you get 3. It's not divisible by 4, 5, 6, 7, or 8. And then it's divisible by 9, okay? So these are all the factors of 24, all the factors of 9. Now what you want to do is keep in mind, you want to take the positive and negative of each of these, basically. So we could write that in, but really I'm going to say, let's just kind of keep in mind that we want to take the positive and negative of all the different combos we can get here, okay? So then what you do is you take basically every combo of these numerator and denominators and write them out as a factor. So thinking about every combo of these two numbers here, we're going to get 1 with 1. So that gives us positive and negative 1. 1 over 1 is 1, okay? Then we can take 1 over 3. So positive and negative 1/3, okay? Then we can take 1 over 9. Positive and negative 1/9. Then we just keep going. So we just do 1 with 1, 1 with 3, 1 with 9, okay? Then we do 2 with 1, 2 with 3, 2 with 9. So that'll give us positive and negative 2 over 1 is just 2, 2 over 3, positive and negative 2 over 9. Okay, and this is obviously going to create a pretty long list because 24 has a lot of factors, right? But we're just going to keep on going, basically. Then we have 3 over 1, 3 over 3, 3 over 9, which is just going to give us positive and negative 3. 3 over 3 is going to give us 1. We already have that here. 3 over 9 is going to simplify down to 1/3, which we already have up here. So we already have that one. Okay, then we're going to take, I'm actually going to kind of erase some of this. This is a little bit much. Okay. Okay, then we go with 4. 4 over 1, 4 over 3, 4 over 9. That doesn't give us anything that we have before, so we're going to get plus or minus 4, because 4 over 1 is 4, plus or minus 4 over 3, plus or minus 4 over 9, and so on. I think you probably get the pattern by now, but you keep going. 6 over 1, 6 over 3, 6 over 9. Keep in mind, though, you want to simplify those fractions down all the way and make sure that you don't get a number that you already had, because if you do, then you don't need to write it again. But anyway, going through this whole process, you're eventually going to end up with a big list of factors. Okay, so this example is a little bit long because 24 has a lot of factors. So we're creating a lot of different factors here in this example. This is quite a list. But what this list represents is all the possible roots or zeros of the original polynomial. Okay, so this entire list is not all going to be zeros, but all the zeros of the polynomial will be on this list. So it's like the square and the rectangle thing, right? All squares are rectangles, but not all rectangles are squares, right? Same idea. All the zeros of the polynomial will show up in this list, but not all the numbers in this list will be zeros of the polynomial. So then from there, what you can do, there's a couple different options. You could either, let's just say, for example, we take x equals 1, right? If x equals 1 is a 0, that means x minus 1 is a factor of the original polynomial, right? Because if we take this original polynomial, and let's say we can break it down as x minus 1 times a bunch of other stuff, right? Some like x to the third term, some x squared term, whatever. You know, I'm not going to show you factoring that out. But you could do polynomial long division, which I have made videos on if you want to go check those out. go to my channel, look for polynomial long division. I'll show you exactly how you can test and figure out how to pull out a specific x minus 1 factor like this, okay? So let's say you do that. If you end up with no remainder, that shows you that x minus 1 is a factor of the polynomial, and that tells you that x equals 1 is a 0 of the polynomial, okay? That's kind of the long way to do it. The short, easier way to do it, much, much, much easier, is instead of going through that whole, factoring out using either polynomial long division, synthetic division, whatever one you want to use, both would work. And I've got videos on both those topics if you want to go check those out. But the easier way, keep in mind what a 0 of a function is. A 0 of a function means if you take that number and plug it into your function, so in this case, if we take f of 1, we should get 0, right? If that's true, then we know x equals 1 is a 0. If it's not, then it's not. So basically what you can do is once you get this whole list, you can take this whole list and start plugging it back into this function and see if you get 0. So let's test f of 1, right? If we take that, we plug in 1 for x. All we're doing is going back to our original function f up here and replacing all the x's with 1s. Okay, so we plug in 1 there, minus 9 times 1 cubed, minus 58 times 1 squared, plus 4 times 1, plus 24. Okay, so there's all the possibilities, or not all the possibilities. There's plugging in 1 for all the x's. Sorry. So now if we go ahead and evaluate this, we get 1 to the 4th is 1 times 9 is 9, minus 1 to the 3rd is 1 times 9 is 9, minus 1 squared is 1 times 58, or times negative 58 is minus 58. 4 times 1 is plus 4 plus 24. And then we can evaluate this. 9 minus 9 is 0. Minus 58 plus 28 is going to be minus 30. So this does not equal 0, right? Clearly, negative 30 is not 0. So that tells us x equals 1 is not a 0 of our polynomial. So basically from there, we've just eliminated, okay, x equals 1 is not one of them, right? Then we can test negative 1. Go plug in negative 1. So obviously this is a pretty exhaustive process. Like I said, this example specifically with 24 and 9 being the factors, or the numbers that we're taking the factors of, there's a ton of different possible zeros in this function. So this example is a long one. Most examples, you may only get 4 numbers in this list. And it's pretty reasonable at that point to go back to your original function f of x, right here, and start plugging in those x values to see if you get 0. And once you do that for every single one, then you've just figured out what all the x values are that are zeros of your original function. So that's really the whole process. I'm not going to work through every single one of these because, like I said, it's quite a list. If you want to do that, though, definitely encourage it. It's good practice. But you could also, jump onto an example that doesn't have quite so many zeros. That might be better. But anyway, that's really all there is to the rational zero test. It gives you a list of all possible rational zeros of a polynomial function, and then you can test each one to figure out which one's actually zeros. So that's it for this video. Like I said, go check out my Precalculus study guide. You can get it right up here. Scan that QR code, check out this link, whatever you want, either way. And let me know what you think of this new style, this new format. Drop a comment below. Leave this video a like if you did like it. Thanks, and I'll see you next time.